Hello, my name is Calder. I'm a grad student at University of Toronto, Department of Medical Biophysics, and I'm going to be talking about open source tools for topological data analysis. So many problems in applied statistics and computer science can be boiled down to this sort of structure, manifold estimation, where we have this smooth structure, as we see in this white infinity curve, but we're sampling it with some noise on top, as seen in these green points. So the objective here is to sort of extract this underlying structure from this noisy data set. You can think of it also as we're measuring the noise, but we expect the structure. So how do we sort of separate these two? And so the approach I'm going to talk about here is called persistent homology, where given this measured data set, we can organize the topological invariants of this data set by their length scale. So lower length scale is over here, higher length scale is over here, and also the distance from the diagonal here corresponds to the importance of said feature. So what we can see here is that we've managed to isolate these two chunks up here, which correspond to the big circles in the data set, whereas all this down here is pretty much noise. So this is sort of the motivation for why you would want to do topological data analysis, to sort of give you this sort of clustering of what features matter. And now I'm going to go over some tools that would help you do these computations in your work. So first, in order to do any kind of topological analysis, you'd want some sort of topologically interesting data sets. And that's where this repository Datasets comes in from scikit-TDA. And I use this to generate my noisy infinity sign. And it's quite a simple function call in Python, where I just import the module and call this infinity sign. They don't have a ton of shapes, but they have enough to sort of get going with your analysis. Now, to actually do this calculation, we need to compute what's called the Vietoris-Rips persistence diagram. And so there's a bunch of different ways to do this, and obviously this is only a partial list, but the ones I'm going to go over are sort of that I've either seen or used. So I think this is a good starting point for anyone who wants to get into topological analysis. So the first one is called Ripser, which is a very fast C++ implementation of the persistent homology calculation. And it's a very good starting point if you want to incorporate this into your own apps or just run the algorithm as fast as possible, although note that this is in CPU. For Python use, scikit-TDA has a Python wrapper for the C++ Ripser, so it's easier to access via Python instead of having to use the C++ source code. Also, if you want to do persistent homology on GPU, there's Ripser++ from Simon Zhang's repository. I haven't used this as much because I haven't really used GPU and parallel computing for topology analysis, but it promises a lot better performance, although there might not be as many features. Finally, for sort of image or voxel-based data sets, there's this cubical Ripser repository, and this is great to give a sort of natural pixel or voxel structure to your arbitrary data set for calculating the topology for. And there's obviously many more. One that I know is GUDHI, that a lot of people use. I just haven't used it myself. Also, we can incorporate persistent homology into neural networks to help them understand the topology of the underlying image. So the first one is Homology CNN, which integrates a basic persistent homology calculation using cubical Ripser into a sort of classification network. And there's also Topology Layer, which is a general purpose PyTorch implementation of persistent homology that you can use for any sort of general purpose network that you would want. Finally, it would be useful to visualize this topology. And the way we're doing this is with Persim, just from scikit-TDA. And you can see that sort of visualizing the diagram in multiple different dimensions here. So on the right, we have persistence landscapes, which are the same thing as persistence diagrams, but just rotated so that the diagonal is on the x-axis here. Also, with these different points, there's different depths of landscapes. So the bigger ones are at depth 0, and the smaller ones at depth 20 or 25. So we have this other natural ordering here, which sort of gives you the biggest features or the biggest landscapes up front and all the smaller features later. So yep, that's my presentation. If you're interested in learning more about topology or in learning about how I'm using topology to make scar maps for MRI images, you can contact me at this email address here. Thank you.